Hi, this is Kevin from the Mathsaurus, and in this video we're going to look at the second half of the short answer questions from the Oxford Maths Admissions Test from 2019. I know there's loads of people out there preparing for the 2020 paper at the moment, or perhaps you're watching this in future years. I'm sure it'll be just as useful. There are playlists going through the 2018 paper in full and quite a lot of the 2016 and 2017 papers that I've made before that I'll link below as well. Check those out over at the Mathsaurus website. Have a look at the Amazon store if you want some extra suggestions for wider reading and things like that. Please do like the video and subscribe to the channel if you're finding it useful. It really helps me get this content out there. And if you click the bell notifications as well, I'm going to try and put the rest of this series out in time for the 2020 paper, so you'll get notifications when the next parts are out as well. So in F, we've got an equation sine cubed x plus cos squared x equals 0, and we want to know how many solutions it has between 0 and 360. So I've just drawn a few sets of axes here, because I think the easiest way to do this is just by thinking about a few graphs. So I'm going to think about, actually, rather than solving it in this form, solving it as sine cubed x equals minus cos squared x. Okay, so perhaps on all of these graphs as well we can think of having points at 90, 180, 270 and 360. So if I started just with the graph of y equals sine x, then we know that it looks something a little bit like this. I'm not going to bother being too accurate here. And so sine cubed x, well, all of these numbers are between 1 and minus 1. So if I do sine cubed x, effectively the points at 1 and 0 stay where they are. And we're gonna, again, everything else is going to get smaller when I cube it. So I don't know, it's going to look sort of something like, it's going to be sort of similar-ish to sine. It's just still going to get to 0 and 1. It's going to have a sort of slightly strange shaped curve in between. You could look at it on a graphing software if you really want to know what it looks like. But actually, this is enough detail for me to answer this question, and you'll see why in a second. Similarly, if we do, I won't write the numbers on here, but these are 90, 180, 270, and 360. If I think about y equals cos x, okay, that does something like this. So again, if I do cos squared x, all right, that's also going to still go through all the ones and zeros are going to be in the same place. And again, it's going to be sort of like damped a little bit, but the negatives here are going to be positive this time. So it's going to sort of, it's going to be sort of roughly something like this. And then finally, if I looked at y equals minus cos squared of x, going through these points, I've just got to try and come up with something that looks sort of roughly negative of this. And notice here that I'm not really worried about the detail of the shapes of this curve, as you'll see in a second. I just want to, because all I want to do now is compare this one on the top here, sine cubed x, and see if it's got any intersections with minus cos squared of x. And you can see in this first, basically in this first quadrant here, if you like, from 0 to 90, sine cubed is positive, minus cos squared is negative, so there's nothing there. And the same between 90 and 180, one is positive and this one is negative. But if you think about it between 180 and 360, sine cubed, if I put it on here, is going to be doing something like this, even though I don't know exactly what the shape is. So I don't have to know where the roots are, but I can see there are going to be two roots here, or two solutions, and I can say that the answer is C without having to do anything any more formal than that. Okay, G is a pretty testing question. In my experience, students very rarely like logarithms, and a question that really involves actually thinking about logarithms in this way is, I think, going to be a tough one. So let's have a look at it. We've got these three log equations, and we want to know if this set as a set of simultaneous equations, they specify the values of a, b, and c uniquely, or just some of the values uniquely, or perhaps they're not solvable at all. And it says that a, b, and c are bigger than 0. I think ideally, if I were writing this question, I might have just made it very explicit that a, b, and c can't be 1 here as well. I mean, it doesn't really make the logarithms don't make too much sense if they are 1, but I think that would perhaps help be specific here. We're not going to take that as a possible solution here. So let's think about the first two. So we've got log a of b and log b of a, right? And you should perhaps you would know that actually this is log a of b is 1 over log b of a. There are lots of ways into this question actually, but this is the way I went with it. Okay, because these are rules of logarithms. So if I said like what's log to the base 9 of 3, well 9 to the half is 3, so that's a half, but log 3 of 9, well 3 squared is 9, so that's 2, and this rule applies in general. Okay, so so you can convince yourself that's true. So actually that means here that c is equal to 1 over c plus 3 over 2, so I've got c squared plus 3 over 2c equals 1, or c squared plus 3 over 2c minus 1 equals 0. So this is 2c squared plus 3c minus 2 equals 0, and you can factorize this as 2c minus 1 times c plus 2 equals 0, so that gives me c equals 1/2 or c equals minus 2, but we know that a, b and c are bigger than 0, so it's not going to be c is minus 2. So at this point we know that these equations do at least specify c precisely, uniquely, and now the question, so it could be b here, maybe there's still infinitely many solutions for a and b, or maybe we can also specify a and b. So these first two equations, now say log a of b is c, but that's equal to 1/2, so that's equivalent to saying that a to the 1/2 is b, or we could use the second one and get log b of a equals 1/2 plus 3 over 2, which is 2, which is saying that b squared equals a, but these two effectively are one and the same thing, right? So we'll just use one of those. So let's take a equals b squared, and if we look at the final equation, then it's log c of a is b, but we now know that again c is equal to 1/2, so this is log 1/2 of a is b, so this says that 1/2 to the power of b is equal to a. So the question is, can we solve these two together to get a unique solution or not? So let's just think about the graphs here. Let's say if I drew a graph of a equals b squared, we'll call these axes a and b, we know what that looks like, something like this. And then similarly if I did a equals b to the 1/2 to the power of b, we've got some exponential type relationship here with the power 1/2, so which is going to go through when b is 0 it goes through 1, and then as b goes to infinity this goes off to 0, and the exponential grows more rapidly than the quadratic here, so this side is never going to meet here. So we do see here that there will be just one point where these two intersect. There'll be a pair of values a and b that will be uniquely specified by these equations. So the answer here is A, that the three simultaneous equations here do specify a, b and c uniquely. Hope you're enjoying this video. Please do like the video and subscribe to the channel if it's useful to you, and share it with anyone else you know preparing for this paper. It really does help me get the content out there, so I'd really appreciate it if you could do that. So in 1 part H we've got a triangle ABC with a right angle at B, so the side lengths are positive numbers in geometric progression. So let's call the sides A, B and C, slightly against the usual convention here of naming the sides with their opposite their letters, but that's fine. Because it's a right angle triangle, we know that it satisfies Pythagoras' theorem, a squared plus b squared equals c squared. And because the sides are in geometric progression, we know there's a common ratio c over b, which is the same as the ratio b over a, where here I'm assuming for a second that a is the shortest side, b is the middle, and c is the longest side. And we'll think about if it's him be the other way around as well in a second, but that's good for now. And what we want to do is we want to know something about tan of angle BAC. Okay, so that's that's this angle here I'll call theta, right? So tan of theta here is opposite over adjacent, so it's A over B, and let me just call that x for the purposes of this argument. So taking these two and putting them together, well, let's take Pythagoras' theorem and divide it through by b squared, right? So I get a squared over b squared plus 1 equals c squared over over b squared, because that allows us now to use this, and if I replace c over b here with b over a, I get a squared over b squared plus 1 is b squared over a squared, right? So if this thing tan theta is a over b, which I've called x, right, this is x squared, and this is 1 over x squared. Okay, so I get the equation x to the 4 plus x squared minus 1 equals 0, and then we can just see this as a disguised quadratic, and then use the quadratic formula. So x squared here is minus 1 plus or minus the square root of b squared is 1 minus 4, so plus or minus the square root of 5 over 2. So now 1 minus 1 minus root 5 is going to be negative, so if I'm going to take the square root here, I'm going to have to just take the positive 1, which is minus 1 plus root 5 over 2, and then take its square root. Okay, and I can do that. Now, so all the answers here have two possibilities, and as I said at the beginning, we do need to just think a bit carefully about whether the angle is here or here, in terms of in the sense that like maybe A is maybe it was actually the other way around, and A is the longer side and B is the shorter side. But if you think about it, that effectively means that this would be my angle theta. So instead of in this argument having A over B, I'm going to have B over A, right? So the other answer is just 1 over x, where that's the answer we've just worked out, right? So that would be 2 over the square root of 5 minus 1 square rooted, and if we just rationalize that, then so I'll get 2 times the square root of 5 plus 1 over 5 minus 1, which is 4. So the other answer here will be 1 plus root 5 over 2, all square rooted, and then that does give us that the answer here is C, and they're the two answers that we've got. Now you could, if you set up the triangle in a different way, you'd end up with a slightly different equation that you'd solve here, right? If you could work out this one first, and if you've done that, I think I've done that here as well, that you end up solving the equation x to the 4 minus x squared minus 1 equals 0 instead, and getting this one out directly, and then you could do 1 over x to get this one, or you could run the argument twice and get the two different solutions. Doesn't matter, as long as you end up with the answer as C here. So if you've spent too long thinking about I, you might find the answer frustratingly straightforward here, although the reason it's one of the last questions here is that there's a difficult idea underlying it, I suppose. It says, can we find numbers x and y, positive numbers, such that x times 2 to the x is y times 2 to the y here, right? So, and x and y have to be different and positive, basically, right? So if you think what this question is really asking, if you thought about this function f of x as x times 2 to the x, it's really saying, can I find values of x and y such that f of x is equal to f of y when x is not equal to y. Okay, and if you just think about what the graph of x times 2 to the x would look like between, for values bigger than 0, well, 2 to the x is going to look something like this, and y equals x looks something like this. So for negative values, I might get something a bit complicated because I'm multiplying a negative by a positive here. But for positive values, they're both just strictly increasing functions, right? So it's going to start at 0 times 1 here at 0, and so x times 2 to the x here is just also going to be an increasing function. So that means that if f of x equals f of y, okay, that means there's basically, if you give me a particular value of f of x, there's a unique inverse point here for the positive, just for the positive values at least, right? So if this is my f of x, then this will be my x, and there's no other different value where I could have the same y value here, but a different x value, right? Different output for the function for the same, different input for the function with the same output, basically. So that means that the answer is that there are no pairs of x and y that satisfy this one. Okay, so the last of the short answer questions is usually pretty tough, and I guess this is no exception. We've got an equilateral triangle, centre O and side length 1, and there's a straight line. I'm going to say there's a straight line through the centre, intersects the triangle at 2 distinct points P and Q, and we want to know what the minimum possible length of PQ is here, right? So now I've just actually put the centre here by just drawing some lines from the vertices to the middle of the other sides. Some of you might shout out, hang on, doesn't a triangle have different types of centre? And actually, yes, there are different centres that we can describe for triangles, but this is an equilateral triangle, so we're okay, and we don't have to worry about any possible ambiguity here. Okay, now my approach to this question is perhaps slightly informal, but it is a good answer, and I think it's the sort of answer that the way you're meant to be thinking about these questions in the real exam. So I'm going to kind of get to the answer the way I sort of fudge my way slightly to the answer perhaps to begin with, that you could kind of go back and check and make rigorous for it. But there was a sense to me actually in which it was, I looked at this question and I thought, well, I can't exactly justify it right away, but I'm pretty sure that the best option here is a line that just goes parallel to one of the sides. And actually this to me somehow, maybe from some intuition I built up here, it was just like, well, I think this is going to be the shortest type of line that we can get there. And you can sort of look at it and you can play around with it, and now you can sort of imagine, okay, imagine I sort of pivoted at the origin here and I made a line that was sort of still going through the origin a bit further away from it, and I'd be like, that one definitely looks slightly longer. If I go in either direction away from this point, I end up with something slightly longer until I kind of get to this option, which is clearly a lot longer. And if it's not going to like increase a bit and then decrease in this sort of scenario, I think, where it's going to the length of this line is going to get longer until it gets to this point, and then if I start getting further, it will decrease again until I get to the next point that's parallel to a different pair of sides, say, right? So I think you can reasonably convince yourself that by making an argument like that this is just the shortest possible line. And perhaps if you want to give me a more rigorous argument that this is the best, you could pop it in the description below. Perhaps the mark scheme gives a more rigorous one. But I think this sort of is how you're meant to be thinking about it in the exam. Now the question is then, well, what is the length of this line? And again, a really simple scale factor argument can tell us this. This length on the side here is 1. The centre of the triangle is like 1/3 of the way up the triangle. I'm not saying it's 1/3 of a unit up, I'm saying it's 1/3 of the way along this line here. Okay, and if you imagine lines sort of going horizontally here, starting with length 1 and eventually getting to length 0, a scale factor argument here is going to tell us that it's going to be linearly, the length of these lines is going to be linearly decreasing. So if I go 1/3 of the way up, I'll have gone 1/3 of the way from 1 to 0, and the length of this line will be 2/3. So the answer to this question is D, 2/3, and then we're done. So tell me if you like that argument below. I think some people are going to say, I want something written out really rigorously. Others might say that's kind of an interesting and neat and quick way of doing it, because remember, that's what we're looking for in maths. It doesn't matter if you get every question right necessarily. You want to be able to do this efficiently, make the most of your intuition, and with the harder ones of these short answer questions, maybe you're going to expect to not get them right away. Perhaps you'll have to leave them and think about them and come back to them later. Very good marks on these papers are nowhere near 100%. And this paper actually had lower boundaries compared to the last couple of years as well. Anyway, let me know what you think about that. But for now, we're done with the short answer questions. So I hope that was useful. Please do like the video and subscribe to the channel if you haven't already. Click the bell notifications if you want to know when I'm putting out the rest of the questions for this paper. I'm going to try and do as much of it as I can before the real MAT exam for 2020. So let me know in the comments what you think about these, and if you've got any other questions or anything else you'd like me to talk about in the next videos.